Greetings, I'm Yvonne Stapp for Science for the Public, and I welcome you to our Contemporary Science Issues and Innovations program. Today's guest is receiving a lot of attention for an innovation that scientists have sought for generations, the extraction of electricity out of thin air. Jun Yao is Associate Professor of Electrical and Computer Engineering at the University of Massachusetts Amherst. Dr. Yao and his team have developed what is called the generic air-gen effect, a device that produces constant stream of clean electrical energy, and it can be used all the time, anywhere. This is a real breakthrough, and we are delighted to welcome Dr. Jun Yao. Thank you very much for joining us.
Thank you. Thank you for the invitation.
Okay, and to get a little bit of background regarding this air-gen effect, apparently there is plenty of electricity in the air, and from space, like from the space station, you can see it. There's lightning all over the place. But can you tell us why there is so much electricity in the Earth's atmosphere?
Yeah, but I think ultimately all the energy sources come from the solar energy. So you can imagine that the solar energy comes in, in the form of light, but the light is going to be absorbed, right?
Right.
So I think it's estimated that 50% of those solar energy actually eventually still goes into space in the form of evaporation. So the water molecule, actually carries this amount of energy in the space. So the solar energy really is the ultimate source of, all kinds of energy on Earth.
Yes,
yeah.
Yes. So it's there. They've known about it for a long time, and now you have managed to do something with it. Anyway, your innovation, the generic air-gen effect, the concept, could you tell us how this extraction of this electricity works?
Okay, I will try to do it in a simple way. So this is, I will try. So this is a simple device, I call it. So it's a thin film. Mm-hmm. And within this film, there are many, many of those small pores. And the pore size is so small that it achieves to the so-called nanoscale. So we call it the nanopore. Mm-hmm. And nanopore is a size about probably less than 10,000 the size of the diameter of human hair. So that's small size. So this film has many, many of those nanopores. So one interface, the top interface, is exposed to the air. The bottom film, the bottom interface is sealed. So now you can see that the air-water molecule can come from the top interface through those nanopores and reach to the bottom interface. But these kind of nanopores, they are so small, right? So the water molecule can easily bump into the surface before they can travel around. So that means the top interface of this film is actually bombarded more often than the bottom buried interface. Now, we actually said before, the water molecule actually is an efficient charge carrier. That's why we got the lightning during the thunderstorm, right? Mm-hmm. So imagine that now when the water molecule hit on the wall of the material, it donates certain portion of charge to the material. So now since the top interface is bombarded more often than the bottom interface, so the top interface will receive more charge than the bottom interface. So over time, you see that there's a charge imbalance build up between the top and bottom interface. The top receives more, the bottom receives less. And if you connect the top and bottom, that will create a charge flow. That's the electricity. So at a certain point, this is kind of similar in a general way to how the charges build up, across the cloud, right, in the sky, top and bottom. And that's how we also got the lightning effect.
I see. And that's really great. Now, it seems like this is a very logical kind of development, but how did you come about developing this? I can see the principle, but how did you come about developing the effect?
So we did not design this. We did not plan on this. In fact, it was a serendipitous discovery, because initially we were working on, let's say, humidity sensor, all right? And we wanted to detect the humidity level in the air. But somehow the student who was working on it forgot to plug in the power. And surprisingly, we still found that there was electrical signal coming out from the device. So we say, wait a minute, it looks like electricity is coming out from nowhere. So that totally diverged our focus from the initial so-called humidity detection to electricity generation from, the air water. And actually, it took quite some time. We initially discovered this phenomena back in 2018. So now it's 2023. So, adding together, it's 5 years, from the initial phenomenological discovery to later on, so, more in-depth mechanistic understanding.
That's great that was serendipitous, a complete accident, and you come up with something tremendous in terms of its potential. And you mentioned here the nanopores that are used for this. Is there a special material, and or can you use just about anything to get this particular structure?
We call it a generic effect. That means, in principle, any kind of materials, if you can engineer these kind of small pores in the material, you can get this effect. But of course, it may still vary in terms of the energy density or efficiency. For example, right, some material, their surface is more interactive with the water molecule. So that means they can generate more charge than other material. But this effect is common. So we call it the generic effect.
I see. And then you also mentioned, at least from the articles that I've seen, there's a special bacterium, but it's not clear, or I wasn't clear, whether to make that nanofilm, whether you had to have one specific bacterium, this geobacter, or you could use just about anything?
So the geobacter really, it was the first bacteria system we used for this kind of discovery, right? So that's the initial material we used for the phenomenological discovery. So the so-called geobacter actually is a type of bacteria that lives in the river mud. And that was actually discovered probably now close to 4 decades ago by my colleague, microbiologist Derek Lovely here at the UMass Amherst. So anyway, this is a type of bacteria. It has a cell body, right? Yeah. But it also has these kind of long filaments, right? We call the protein nanowires. It's like on your head. Yeah. You have lots of hair, right? Right. The only difference is that these kind of filaments are so small, it probably is 10,000 times smaller than a human hair. So that's why we call them a nanowire. So it's nanoscale wire structure, nanowire. These bacteria, they use these kind of nanowires for communication with the environment. For example, they can, it's like a cable, right?
Yeah, yeah.
So they can use these kind of cable to communicate with its own species or with the environment. So Derek Lovely, he developed a certain kind of clever ways that you can basically share off these kind of nanowires and purify them. So imagine now you have bunch of those nanowires, all right, billions of them. And if you put them together to form a thin film, now you can imagine that between these wires, all right, these wires, there naturally forms certain kind of orifice, right? That's the nanopore. So in a thin film that contains many billions of those protein nanowires, it also contains many of those nanopores at the wire interface. So that's the initial material we use for this kind of discovery.
Okay, I may not be quite clear. Do you need this particular geobacter? That one that's the preferred one, but you need that to do this. Then
not necessarily. Later on, we don't need to use the bacteria. We don't need to use this specific material. So you can use any kind of other material. For example, there's a kind of a fiber. It's called cellulose, which really is the material that compose, for example, the wood, right? The tree trunk. So yeah, so you can also extract a certain kind of small filaments. It's called a cellulose nanofiber. And you can use these kind of nanofiber to assemble a thin film, which essentially structure is kind of similar, right? It's small filaments, and between these kind of filaments, there's nanopores. So you can also get this edging effect. And later on, you can use other materials. And for example, if you can have these kind of tiny little bit, we call it nanoparticles, right? Little particles. Now you can imagine that you put these kind of little particles together. Between these two particles, it naturally forms these kind of nanopores, right? So a thin film assembled from nanoparticles can also have this effect. So that's why we call that this is a generic effect. It no longer is exclusive to certain kind of material.
Good. That sounds extremely promising. That's very clear this time. Now, the other thing is that you've known about the electricity in the air for ages, and I think Nikola Tesla pointed out that the air was full of it, and he couldn't figure out how to extract it to use it for anything. And you mentioned that this was an accident, actually, that this discovery was a kind of an accident. Is it possible that you would have to have this particular era where we have nanotech and so on in order to develop this kind of technology? It had to be a particular period in history when the capability could be realized.
So if you look at the aging mechanism, as I explained before, so really the key element is to make these kind of nanoscale pores in the material. Now, I think this is less possible before, right? Before the nanotechnology era. So that's why I think probably this is the right timing that we have this chance to discover this, because before we actually didn't know how to make these kind of nanoscale material.
Okay.
I think that probably is
And it's essential that the nanotech part of it is essential. That's the thing. Is that it?
Correct.
Right. And I ask because it seems like nanotech has opened up all kinds of possibilities. Every time you turn around, there's something new developing, and I'll bet you in your lab this will be happening or has happened already too. But this one is getting a great deal of attention and seems to deserve it, and it's very interesting that should happen in our time when we really need it. A couple of things about this. Apparently, this is available anywhere. You can use this anywhere in the world. You don't need to worry about the weather because it can be indoors, it can be in anything, it can power phones, it can power houses, whatever. Is that the case, that it can be used anywhere?
So in principle, it is, because we tested that the device can function in a wide range of the relative humidity, for example, between 20 and 100%. So I Googled, and it says that the Sahara Desert actually has a relative humidity level of 25%. So that still falls into the range. But I think realistically, you don't want to deploy this device in Sahara Desert. You'd rather deploy it in the rainforest where you have much higher humidity, right? So that's going to give you much higher power output. Well, I think the beauty thing is that you don't need to cut off the trees to deploy this.
Okay.
Right? So, for example, if you want to deploy solar panel, you need to cut off the tree.
Yeah. Right.
This thing, you can naturally blend into the natural environment without causing the detrimental effect. That's why I call this is a greener technology.
Yeah, the greenest.
It can naturally blend into the environment. Okay. So I think that's the excitement vision, at least at this stage.
Yes, yeah. It does sound, from what I've read, as I said, that you can just use it anywhere. You've pointed out now, well, it's easier to use it where you have high humidity, but that's just probably a temporary thing anyway. In terms of scale, one of the things about innovations that we see frequently is that there's a big difference between what you can do in a lab and you create a new device and so on, but it doesn't scale up well. But I wonder if this will this scale up? So give us an idea of what the device size would be now and what it can take care of, what it can power, and what you would hope for it to do, and will it scale up?
All right. So usually there could be certain kind of simple principle to tell if a device can be scalable or not. So for example, if one battery, and if you connect the two batteries, you find that the power output twice of the one battery. So that means the battery is scalable. That's why we pack many batteries in a Tesla car, right?
Yes,
so that you can drive the Tesla car. So this is simple. We find that if you have a tiny little this agent device, one device, and you have two, you put them together, you double the power.
Yes.
So that means it's scalable, right? Fundamentally, it is scalable.
Okay.
Now it's more about the strategy, how you're going to put them together in a very efficient way to scale up. So that's called the scaling technology or technique. And there's a way for that. At least we have certain kind of engineering theme already. It's that we haven't gotten into the phase of development. And I can give you certain kind of general idea. So for example, the solar panel, right?
Yes.
It's scalable. You can make a large, area of device. So this thing is the same thing, right? So you can make a large thin film, and you can put on an electrode that does not block the humidity.
Yes,
so
right.
You see that the solar panel relies on an electrode that does not block the sunlight.
Yes.
In this case, we need an electrode that does not block the humidity, and which is actually easily achievable. So that's the way to make it larger. Now, that's not the end, because in a solar panel, you cannot stack them up, right? Because the first layer is going to block the sunlight. And so solar technology it's intrinsically planar technology. But this agent is 3D technology, which means that you imagine that the air is diffusive. It's not incidental, it's diffusive. It can come in the lateral way. So which means that in principle, you can stock many of layers in the vertical space to increase the power without taking up additional footprint. So this is like we building up high buildings in a city, right? We have limited space, but we can develop in the vertical space to accommodate more population. So this is the same thing for aging. The beauty is that you can go into the vertical space to increase the power density without taking up additional space.
Right. At this time and how in the near future, how much can it power? If you could you build one large enough to power a building for an apartment building or an office building yet, or in the foreseeable future?
Okay, I want to put this clear, lest that people have wrong expectation. Currently, in the lab scale, we only made called a prototype demo device. It has the size of a human fingernail, and so it can power a tiny little, let's say, LED dot.
Yeah,
it's like an LED dot. It's tiny little power, but the device is so thin, so it's only about 1/5 the thickness of a human hair. So we did some rough estimate. If we can make the device like, let's say, 1 cubic meter, so that's the size of, for example, a refrigerator, right? And that can give us about kilowatt level power. So what does that mean? If you dump this kind of box anywhere in your backyard where you don't need the space, we call it you use the waste space, all right? Dump that in your backyard. That essentially can suffice the electricity usage in typical household.
Okay.
That level of power. And you can imagine if you further increase the size, that can certainly, the power can still go up to the possibility of powering an entire building, for example.
Yeah, right.
So if you have a much larger device volume. So, but I still wanted to emphasize that these are really ideal estimate.
Right.
We haven't yet, gotten even close to that device level.
Right. No, I understand that. It takes time to develop that, but in principle, that is doable. That's the thing. The other thing is that it sounds like it's something that could be built and used anywhere in the world. You wouldn't have to put in elaborate wires or anything like that. Is that the case? In other words, in developing nations and stuff where they might not have a lot of facilities to support, this could be used in separate buildings and so on, and simply be available. Is that correct?
Yes, I think that's probably the beauty of this technology, because I mean, in many poor or remote area, the challenge of delivering electricity there is the infrastructure, right? You need to construct lots of network, connecting there. That's a big challenge. But if this provides a neat portable electricity, so you don't need to build up this kind of infrastructure network. So I think if this can be scaled up, this could be a very attractive solution.
Absolutely.
To the powering of those kind of remote or poor area.
Right, and then it would be basically free. It's easy to provide. It sounds terrific. And when do you think this, can you give an idea, like within a decade, do you think that we would see this used more broadly?
That's where I need to be careful. I don't want to cause whatever. Either you're gonna depress people's excitement, or you're gonna pick up people's too high the expectation. But But I think, I mean, it's useful to take a reference to the solar panel, right? And solar panel actually,
Right.
I think the development of solar panels started back in the 1970s.
Yes.
So it took
Yes.
about 2 decades
Right.
to eventually make a solar panel commercially available. So I'm not inferring anything. I'm not saying
Right.
that
I
this is going to
understand.
take two decades or whatever. But what I wanted to say is that usually technological development can take a good amount of time. From the technical validity to commercial viability, I
Yes.
think there are actually multiple elements beyond even my understanding. So I
Yes.
think in the end, multiple forces really needed to join together to make it happen.
Yeah, it often seems like it's easier to do the inventing and then it takes forever to get it in place, as you say, that because of, well, you have all kinds of legal and other kinds of things in the process of getting this on everybody's plate, so to speak. Anyway, I hope we see it soon. It's fabulous. And then, Dr. Yao, you have done many marvelous inventions, a lot of breakthroughs, and I'm just curious, in our last few minutes, would you please just give us some ideas of other things that you work on that you've been very interested in?
Yeah. So that's interesting. I don't want to pick up which one I like the most because that's going to hurt the
Yes.
student who's working. All right. So we do have other things going on in the lab.
Yes.
In one area, we're developing very tiny little sensors. It's smaller than the size of a single human cell. So that sensor can be, for example, embedded into the human tissue and listen to what's going on in the cell, and so tell you the cell state. So in the end, this could be a kind of very in the future, for example, for
Yes.
disease detection
Yes.
or drug testing. So this
Yes.
is one area. The other is that we are developing the so-called brain mimic computing devices, right? So current computing devices, it's not really brain-like, although we know that they're very powerful, but they actually consume a lot of power. But the brain actually uses much less energy and doing much more fabulous work. So we are making tiny little devices that's more like brain-like. So we wanted to go into that direction to see, can we fundamentally improve the computing efficiency in the future?
Wow, that's awesome. I'm really interested in that. I'll be back. That is, yeah, I know that's an area of development, but that happens to be very interesting. And also that sensor that will open up all kinds of possibilities in medicine, I take. That'd be certainly one area that's very important for it. But I know that you do these remarkable things, and I appreciate your sharing them with us. And I wish you the very best in terms of developing the AirGen effect, and I hope we see it out there in the world. It will really save a lot of difficulties. And so, Dr. Yao, thank you very, very much for joining us today. It was a great pleasure to talk with you.
Thank you, Yvonne. Thank you for the invitation, and thank you for giving me this opportunity to have the conversation, and I really appreciate it. Thank you.
Very enjoyable. Bye-bye.
Yeah. Bye for now. Bye.